So, welcome everyone. Today we will be solving some of the potential IIT JAM questions and some of the questions from the previous years as well to give you a little bit of revision of what's needed. Like we have seen a theoretical portion of these things, uh, like what to do, what not to do. So today we will be seeing some of the problems and yeah. So if you have any more questions or doubt, then you can ask. We will be happy to answer those questions. Okay, so let me start with one of the questions from the last year of IIT JAM. So if so this is IIT JAM question number 9. So if you look at this question number 9, then it says that, so it says if you take pk, so this is the vector space of all real polynomials in one variable. So this is the vector spaces or vector space of all real polynomials in one variable of degree less than or equals to k. All right. So now a linear transformation is defined like this: p from p2 to p3. So it's defined like this, that f goes to f double prime plus xf. So that is how it's defined. If I just write it down in problems, I mean, like, in terms of math symbols. So the question is, which of the following polynomial is not in the range of t? So which of the following polynomial is not in the range of t? So to understand something which is in the range, what do we need to understand is that how does t of f looks like? Okay, so if now I'm taking fx in p2, so then by this definition, p2 is the vector space of all real polynomials in one variable of degree less than or equals to k. So that means this uh, is the vector space of all real polynomials of one variable with a degree less than or equals to 2. That means if you take f of x, then typically it looks like this, where a, b, c belongs to R. So typically it looks like this. Now what you need to understand is that where is this getting mapped by t? All right, and with that notation, with that notion, you will understand that which of the following polynomials is not in the range of t. So the options are like these. So if you have, the first thing is x plus x square. Secondly is x square plus x cube plus 2. Thirdly, it's x plus x cube plus 2. And lastly, it is x plus 1. Now, there are ways that you can actually do it. Okay, so what are some of the ways that you can try to solve it? So one of the thing is that you construct the matrix of T. All right, so now if you construct the matrix of T, so suppose this is the matrix that you have, so this is your TA. So then what will be the vectors in P2? So the vectors will be these A, I mean kind of the way it's getting defined. So see, if you have the matrix of T, first of all, so the matrix of T, the one thing that you need to look out for here, that what is the dimension of P2? So the dimension of P2 is 1x x square. So that means it is 3. So this is 3 dimensional, and P3, this is 1x x square x to the power 4. This is 4 dimensional. All right. So with the help of this, suppose if I construct the matrix, then this will be what? This will be a 4 cross 3 matrix. Okay, so this will be a 4 cross 3 matrix. Let's say for the sake of it, I write this matrix like this. Since it is 4 cross 3, you get the idea. Okay. Now, what will be those polynomials that are in the range? So the polynomials that will be in the range, it is sufficient if you take this vector. So constructing the matrix, if you multiply it with the basis vector, you are going to get the you are going to get the range, which kind of generates, which kind of indicates that what will be the sort of polynomials that will be in the range of your T. Okay, so the key idea is here is to construct the matrix, like how this matrix is going to, I mean how this matrix is going to take place. So once you understand what the matrix is, then T of f of x is nothing but Ta into fx, but now you take your fx as vectors. So that means what? Suppose if you have ax square plus bx plus c, then you take your vectors as c. So this will be your now c, then this is your bx, this is your ax square. Okay, so it is like this. So producting this with this vector is same as understanding the range of your T. So I will construct the matrix, but after that I will leave it up to you to kind of try to formalize which of the polynomials will not be there. So as you see, this is f double prime x f, right? So now let me write it again. So it is from P2 to P3. So this is f goes to f double prime plus xf. So that means I will first understand where these basis elements will go, because that will, like the last lecture, if you have followed the last lecture, that is exactly the thing that will tell me where it is getting mapped. So if I take 1, so of course the constant polynomial 1, this is 0, but this is x. If I take x, this goes to, again the first thing is 0, the second thing is x square. Now x square will be mapped to, so f prime is 2x, f double prime is 2, so 2 plus x is cube. Now whatever you have here, you will need to write it down in terms of the linear combination of basis of P3. So what is the basis of P3? The basis of P3, this is 1x x square x is cube. So how can you write x? So this is actually x, right? So this is x, this is x square, this is x cube plus 2. How can you write it in linear combination of these? So the one way to write is, so 0 into 1 plus 1 into x plus 0 into x square, 0 into x cube. So now how can you write x square? 0 into 1, 0 into x, 1 into x square, 0 into x cube. How can you write 2 plus x cube? This is 2 into 1, 0 into x, then 0 into x square, then 1 into x cube. So the matrix that you have, as we have discussed, so it will be 0, 1, 0, 0, 0, 0, 1, 0, 2, 0, 0, 1. This matrix transpose. Okay, so that means my T of A is precisely this: 0, 1, 0, 0, 0, 0, 1, 0, 2, 0, 0, 1. So now you have the matrix. So now what you need to do is you just need to put these things, like if you have C bx ax square, where does these things go? Under mapping. Okay, so the moment you understand where it will go, so you will see that since this is 4 cross 3, there will be vectors here, but now you understand how we are actually treating the vectors, right? So we are treating the vectors is kind of in the coefficient manner. So this is 1, this is the x, this is the x square part. So just like this, here you will have 1 x square x cube part, and once you figure out what 4 of these are, you just compile them and see what is the result. So the key thing here is that if you want to solve it in this method, the key thing is to understand the matrix construction of the linear transformation. After that, it is just product of matrix. So as I have told you before, you will find these type of matrix representability problems in IIT JAM. So now let us move on to one of the questions from the quiz. So but the fact is that suppose this was one of the questions in the quiz. So if for some k we have a to the power k minus identity equals to 0, then a has to be diagonalizable. Okay, so this was one of the questions. Now let us see. Okay, so one of the examples that you should keep in your mind whenever you are going in any competitive exams for these type of setup is an example like this. So suppose if I take this matrix and I square it, let's see what happens. So if I square it, that then this is 0, 1. So the first entry is 1. The second entry is 0. So in the second row, the first entry is 0, the second entry is 1. Do you see this? So this is in general always true. So if you have the reverse diagonal elements as identity, so that cross that matrix, if you take to that particular power, it will always give you identity. Okay, so what am I saying? So if you have any matrix of this form, 0 and 1, 1, 1. So let's say this is an n cross n matrix. Everything else is 0. So let's say for 3-dimensional case, I'm talking about this matrix. Sorry. So if you have this matrix in 3 cross 3, then cubing it will give you the identity matrix. Okay, so this is the thing, that apart from the diagonal, everything else is 0. The reverse diagonal part is all 1. So that is kind of the reverse identity matrix, reverse diagonal identity matrix. Because if you take any identity matrix, it goes like this. But if you take the reverse of it, it goes like this. Okay, it's kind of the mirror image kind of. So if you take this type of matrix and you take a to the power n, this will always be identity. Now let's see what happens to this type of matrix. Now if I take this as my a, so let's take this as my a, 0 1 1 0. So now the first thing is that you need to understand what are the eigenvalues of this matrix. All right, so if you put down the eigenvalues, so how does it look like? So this is lambda square, because I mean this is, if you are computing eigenvalues, then this is a minus lambda I. So then this is minus lambda, that is lambda square. So then lambda square minus 1, right? So that is the characteristic equation, because if you put here, then this is minus lambda, this is minus lambda. So minus lambda is lambda square, then 1 1, this is minus 1. So what are the roots? So the roots are plus minus 1. Okay. So one of the things that you need to, I mean, it's not very related to this problem. So one of the things that you always need to understand, that if you have an n cross n matrix and all the eigenvalues are different, then it is different and of algebraic multiplicity 1, then that matrix is diagonalizing. So one of the things that why I constructed this matrix is that, suppose you have been given this type of matrix. So now you know that this type of matrix has plus minus 1 is, I mean, for 2 cross 2 it is plus minus 1. For 3 cross 3, you will see what happens. Okay. So suppose if you take 3 cross 3. So if you take 3 cross 3, so then this is what? Minus lambda. Then you have 1 minus lambda, then minus lambda. And you have here 1 0 0 0 0 sorry 1. Now if you try to construct the eigenvalues of these, it is this, I mean, we are trying to construct the eigenvalues of this matrix. So what does this, how does it help? So it's kind of like this, that you have lambda square into 1 minus lambda. So the first thing, sorry, so if I take the determinant, so this is minus lambda into 1 minus lambda minus 0. Then it is the 0 part, minus of 0, then plus 1. So the 1 part is 0 minus 1 minus lambda. So then you see that this is, the first thing is that lambda square 1 minus lambda plus lambda minus 1. Okay, so then from here onwards you can also check that how it, I mean, what are the roots, right? So from here, so if you write it down as minus lambda square, lambda minus 1 plus lambda minus 1, then you take lambda minus 1 common. So these are computational things, 1 minus lambda square. So from here you get, the thing is that if you take lambda minus 1, then 1 minus lambda is 1 plus lambda into 1 minus lambda. Okay, so then what are the values of lambda? So the values of lambda are either minus 1 or 1, but now there is a multiplicity that is going on. So as you can see that 1 is occurring twice. Do you see that? Because so algebraic multiplicity of lambda equals to 1 is 2. So now the matrix that I had chosen was something like this: 0 0 1 0 1 0 1 0 0. And now if I take minus of 1 into identity, how does it behave? So this behaves like this: minus 1 0 1 0 0 0 1 0 minus 1. So this is what will happen, right? If I take this minus 1 into the identity matrix. All right. Now the one thing that you need to look here is that what is the rank of this matrix? So what is the rank of this matrix? So the rank of this matrix is, you can see this, that this is actually 1, because if you just take this column, then multiply it with 0, you will get the second column. Multiply minus 1, you will get the third column. So the rank is 1. Hence the nullity is 2. And that is precisely what we have as. So for algebraic multiplicity equals to geometric multiplicity for all lambda is if and only if condition for diagonalizability. Now algebraic multiplicity is same as geometric multiplicity here, because the algebraic multiplicity of 1 is 2. The geometric multiplicity, that is the nullity of this matrix, it is also 2. Okay, so now if you take lambda equals to minus 1, you can see what happens. Now the one thing that I want to make sure of this example, that whenever you take these examples, these matrices have very nice properties. So one of the things is that it is a to the power n is equals to identity, and diagonalizability kind of follows. So let me finish this up with minus 1 itself. So if you take now, if you take this matrix, you take this matrix 0 0 1 0 1 0 1 0 0, and you do, and you take your lambda to be, now you're taking minus 1. So now this is your plus 1 into identity. So what does this happen? So what the matrix that you have now is 1 0 1 0 1 0 2 0 1 0 1. Okay, now the thing is that these two are same, and this is linearly independent, hence this has rank 2, thus nullity 1. Hence the algebraic multiplicity of lambda equals to minus 1 is same as geometric multiplicity of lambda equals to minus 1. Hence these type of matrices, if you now apply induction, one of the remarks regarding this question too is that, so whenever, so these are actually remarks, so whenever you have these type of matrices, this will always be diagonalized. Okay, so these type of matrices are always diagonalizing. Now what is the catch in this problem? So if we are not able to construct matrices like we used to construct for disproving something, you need to look carefully that what is written. So now there, so from here what do you have? So from here now we will dive into the section of minimal polynomials and characteristic polynomials. So it has been given that a to the power k minus identity is equals to 0. Now what did we learn in our last lecture is that if there is a polynomial such that, so if there exists a px such that p of a is equals to 0, then the minimal polynomial mx will always divide px. Okay, and what do we know about mx? So one of the things is that the mx is the least degree polynomial to divide the characteristic polynomial. This is the first thing. And the second thing is that m of a is always 0. And combining these two things, I will just write it as a property, is that all the eigenvalues are in the minimal, or all the eigenvalues are also the minimal polynomial roots. So now the thing is that if I had said in this question is that A is a complex matrix and it has complex entries and this is happening, then A is always diagonalizable. Can you see why? So the reason that A, suppose now let A be in MNC. Okay, so the moment you have a to the power k minus I equals to 0, so if, so that means what, my p of x is x to the power k minus 1. So that means the root of p of x are all the kth roots of unity. So roots of p of x are all the kth roots of unity. Okay, so now if mx divides p of x, that means what, some of the kth roots of unity are also there in mx. Okay, so how do you express this? So how do you understand that, I mean, what to do with this information that if mx divides, so you know that a polynomial is diagonalizable if and only if mx is split with no repeated roots. Now from here, can you guarantee that your mx will not have any repeated roots? So my point is that suppose you take something like this. Okay, so suppose you are taking square of these. So let's call this omega is the kind of the third root of unity. So if you do this, then what do you have? This is omega square, then 0. So this is 0 0. So omega square, then this is 0, then 0 0. So then you will have 0 omega 0. lastly 0 omega square. So whenever you have let's say whenever you have a diagonal matrix, if you multiply it with itself, it's kind of the squares of each element. All right. So that means what? If I pick this up, if I take this kind of in some way, then omega. So if I write it as omega a, so this cubed is giving me identity. So what you need to understand in this problem is that if a to the power k is equals to I, then what about the minimal polynomial? So suppose for an example, if you had x cube minus 1 equals to 0, so then this is x minus 1 into x square plus x plus 1. So now if a belongs to M3C, what are the possibilities of minimal polynomials that you can think about? The possibility of minimal polynomials are, so now possibility of minimal polynomial in this case is what? This is either x minus 1 or x minus 1 into x minus omega, or x minus omega into x minus omega square, or x minus, so or the entire thing, x minus 1, x cube minus 1. Okay, but in all of these cases, so the fact is that if a to the power k is equals to I, and this is a is in M3C, this you can write it as x minus 1 into x minus omega into x minus omega square. So in each of these setup, do you see that the minimal polynomial is getting split and it does not have a repeated root? So that means that whenever you have x to the power k minus 1, then how does it look like? So if you break it down completely, this is product of x minus zeta p's, right? So where's, or zeta k's, so where zeta k's are the kth roots of unity. So no matter whatever the composition you take, the minimal polynomial will always split if you take your matrix in M3C, MNC, because if you take it 4, fourth roots of unity, then this is what? This, then zeta 1, zeta 2, zeta 3. So this is the equation in fourth roots of unity. Now, minimal polynomial has to be a divisor of that. So no matter what combination you take, it will always be a split and with no repeated roots. Thus, the catch in this question is that if if A is complex matrix, then you can surely say it is diagonalized. But suppose A belongs to, let's take it till M3R. So now if in M3R x cube minus 1 equals to 0, that means there is a possibility. So there is a possibility that the minimal polynomial is x square plus x plus 1, because this is a divisor. So you can construct a matrix whose minimal polynomial is this. Okay, it's fairly possible. You can construct a matrix whose minimal polynomial is kind of this. All right. So, but the thing is that since the minimal polynomial actually has to have every root that has in the characteristic polynomial, So one thing here, what I want to make sure understand is that the polynomial that is given here, I have never said in the quiz question that A is a k cross k matrix. Okay, so the characteristic polynomial might have lesser degree than this. But what am I actually saying here is that the mean, if since x cube minus 1 is 0, so forget about A belongs to M3R. So if x cube minus 1 equals to 0, then there is a possibility that the minimal polynomial is x square plus x plus 1, because of this property that we have just discussed, that if there exists a px such that pa equals to 0, then the minimal polynomial divides it. So now suppose A is in R. So let's say A has real entries and is a member of M2R. Okay, so then having this as minimal polynomial, now we all know that x square plus x plus 1 is irreducible over R. So this is not reducible. Thus, the minimal polynomial will never be split. So there is a possibility where you can find a matrix which is x cube minus 1 equals to 0, but have minimal polynomial as x square plus x plus 1, which is not splitting over R, and thus it might not be diagonalizable. Okay, so this is one of the remarks that I wanted to make in this problem. That's why it might have taken a little bit of time. But the interesting fact is that how we use the splitting criteria of minimal polynomial in these type of problems. Okay, so from here, if we want to write it down, the exact answer. So if we want to write down the exact answer from here on, so it is if A belongs to M to R and the minimal polynomial m of x is equals to x square plus x plus 1, then over R, A might not be diagonalizable. Okay, so that's what we have. So this was one of the questions from the quiz. So the reason that I set these up is because if you look at the IIT JAM question number, so 21, question number 10. So if you look at question number 10, what it says is that, so I will put down the question number and you can understand from the previous uh, discussion. It's like, so the question is let n be greater than 1. So if A belongs to M and C, then they have given two statements. So the first statement is if A to the power k is in, then all the eigenvalues are kth roots of unity. And from the previous discussion, it is, because if you have then A to the power k minus in is 0. So from the previous discussion, you can see that since it is in Mn of C, then the minimal polynomial has to be a multiple of this. And the moment minimal polynomial becomes a multiple of this, and since it is on C, it splits. And thus it will contain all the kth roots of unity. I mean, not all the kth roots of unity, but the eigenvalues will be kth roots of unity, regardless of what my key I am actually taking. K might be greater than 1 or less, greater than n or less than. The next is, so if for some integer k greater than 1, all eigenvalues of A are kth roots of unity, then a to the power k is in. So, but this is not true, because if all the eigenvalues of A are kth roots of unity, then by the previous discussion, you know how does the minimal polynomial looks like. Now, the minimal polynomial looks like that, but that does not give the guarantee that this will always hold from the other direction. Okay, so it might happen. So for some k greater than 1, all eigenvalues of A are kth roots of unity, then a to the power k is equals to in. This might not work, because you can actually have I mean, you can, by the previous discussion, you can kind of construct these matrices with minimal polynomials. Okay, so this one then becomes false, and this becomes true. Okay, so now let us move on to one of the questions from the quizzes, which is kind of important. It is kind of important as a property. So this was the quiz question number 13. So quiz question number 13, it essentially says that R rank of similar matrices the same. So the answer is yes. So if you take A and B, if A, B are both similar matrices, then they have the same rank. So one of the ways to understand it, I will just give you the sketch of the proof. So if A and B are similar, that means what? That means there exists an invertible matrix such that matrix P such that P inverse AP is equals to B, right? So yeah, I mean, in short, AP equals to PB. So this is what similarity means. Now the catch here is to understand is that if P is invertible, then what is the rank of AP? So now as you can see, if AP is equals to PB, if these two matrices are same, identical, then their ranks will also be the same. So their rank will be equal, right? So what is the rank of AP? So to understand the rank of AP, you need to understand what is the nullity. So let's just say that, I mean, both are n cross n matrices. Okay, so A, B, P all in some n of F. So now if you look at, so let's say something like this, that let X belongs to kernel of B. So which implies that Bx equals to 0. Okay. So if Bx is equals to 0, then P B X, this is also equals to 0 because P of 0 is equals to 0. Alright, so this implies that X is also in the kernel of PB. Now, if Y belongs to the kernel of PB, which implies PB of Y is equals to 0. So then from here, the key thing to understand is that will Y belongs to, or let's say where Y will belong. Okay, so if kernel of PBY is 0, this implies, sorry, if Y is in the kernel of PB, then PB of Y is 0. This implies P inverse PBY equals to P inverse 0, which is practically B of Y equals to 0, which implies that if Y is in the kernel of PB, it implies that Y is in the kernel of B. All right, so that means that kernel of PB is same as kernel of B. So this implies rank of PB, rank of PB is same as rank of B. Now, similarly, you can prove that rank of AP, so the same way, I mean, you can actually use the same trick. So then you can try to prove that rank of AP is same as rank of A. So then similarly, rank of AP is same as rank of A. So the moment you have this and you have rank of AP equals to rank of PB. So the moment you have both of these two things, you can conclude that similar matrices have same rank, and this is something of which is a very useful tool to keep in mind. Why am I actually telling that this is a very useful tool to keep in mind? It's because similar matrices, unitary matrices, sometimes you will be given, sometimes you will be given problems where you need to figure out, will these be uh, matrices of same rank? So sometimes it falls that are they of same rank, are they similar? So like there might be ways to prove two matrices are similar, which might prove less difficult than to proving two matrices of same rank. Okay, so with these 3-4 problems I end today's discussion. uh, so next time we will come with some revision setup of the real analysis portion. So thank you for joining. Goodbye.